Can you hear me okay? Yeah? Great. Awesome. So yes, it will be a little bit of an introduction, but introductions are a little bit boring, and I've done this talk like 2 years ago, and I kind of got bored from the introduction one. But it will be on how to use R for machine learning. It will be a code, but I also will explain some concepts of machine learning. So just for my curiosity, who has ever worked with R? Okay. Well, let's see what we can find out for you. Who has been to my previous talk? I mean, today. Oh, crap. You know all my jokes. Okay, that's fine. I just need to figure out something else. So who am I? For those of you who haven't heard, I'm a data science freelancer. I'm ex-Microsoft, so probably on the leaflets I still have it on my badge that I'm from Microsoft. It was when I was submitting the talk. So today I'll be talking to you about R and how to use it for machine learning. We'll go through 3, well, I would say classic machine learning algorithms. So classification, regression, and clustering. And if you're curious about the code, I will show you snippets of the code, the most important parts, but all of it is in a GitHub repository, so just grab it, use it. If you've ever worked with R, you probably don't even need it. So what's the agenda? First, I'll tell you what I think machine learning is, because you know there are thousands of definitions all over the internet. Then I will explain a little bit about the R platform and how I started, and then we'll jump into the code and specific examples. Okay, for those of you who have been to my talk, you know what's coming. So who can tell me what machine learning is? This time I won't cave. Yes, yes. Matrix multiplications. That was for deep learning. You're just repeating my joke, but yeah. Sure. What else? Machine learning. Come on. What's machine learning? Transforming inputs to outputs. Okay, also the answer from the morning. Okay, yeah?
Trying to make machines, make smart decisions.
Trying to make smart decisions. Yeah, so very good. All good answers. Machine learning is not robots, it's not AI, although machine learning is a part of AI, or AI is part of machine learning. Depending where you go, people have different things. So I will try to explain to you what I think machine learning is. It's very, very down to earth and not really that magical. So imagine we have a problem. We have a list of 5 movies, we have a title, and someone went through the effort to count how many times people kissed during that movie, how many times people there was an action, people kicked. And then they applied the labels, so the genre of the movie. So then we have a question. What is the genre of Gone with the Wind? Any guesses? Come on, action or romance? Romance or action, yes. I put this specific example deliberately because we people, we don't think like machines. We don't even, you guys didn't even look at this list. You didn't learn from this data. You just was thinking what Gone with the Wind is a kind of a movie, right? What machines are doing is something different. Machines are getting numbers, and machines are calculating stuff. And machines are getting 5 examples. Those titles are basically like IDs. They don't mean anything to the machine. Despite what those AI people are telling you, machines don't understand text. They can process text, they can get information, they don't understand it. So there's some kind of an ID. We have 2 features of numbers. We have labels applied. And then you have a task. Feature 1 is 31, feature 2 is 4. What is the label? B. Why?
Numbers are sort of similar. 31 is more like 24 and 17. And the 4 for feature 2 is 4 is like 2 and 3.
So you went through, yeah, exactly. So us as people, we went through those numbers and we've noticed that feature 1 has big values and small values for the class B, right? So we kind of like recognize this pattern. And this is what machine learning is doing, trying to recognize the pattern. But it works completely different than what we just did as human beings, because we had it like embedded and nobody actually knows how does it work. Machines, on the other hand, they have just mathematical formulas. So let me ask you another question. What if we have not 5 but 500 examples? 5,000 examples. How would you, as a human being, having those two features, how would you approach this problem? See, it's starting to become something for the machine, not for a human. So one of the things we could think of is to try to visualize it, like put the different colors into different labels and then trying to find this pattern. And it works awesome if we have 2 dimensions. If we have 3 dimensions, kind of starting to become a problem. 4 dimensions, we're starting to get a headache. Very often we have data that have thousands of dimensions. And again, this is where machines are better than humans, because they don't have to imagine stuff. They just have to calculate stuff. So the whole point of machine learning is to find those rules and to find this line. It could be a very complicated line. The line may not be even possible. Maybe those data are not linearly separated. And the whole point of a machine is that a human being is telling the machine, find me the rule, which is of the shape of like this, and tell me what is the number, or what is the threshold, or what is the shape of this line that distinguish my class A from class B. For more complicated examples, it will be more complicated model. This is a very simple one. So, as you've seen through this, when you went through this list, our mind did this kind of automatically. With the machines, as humans, we have to apply this algorithm. We have to tell the machine, use this algorithm and adjust the coefficients. So I will give you the example how I'm not breaking the code of conduct. You can go online and check. This is a very lucrative job. You can earn like 45K. Chick sexers are people that are getting chicks when they're very small. Apparently you cannot tell what's the gender, what's the sex of the chick. And there's this problem. Nobody knows what's the sex of the chick. And I actually learned this example from QA. So, you know, you have chicks, girls and boys, they have different fate. If you separate them wrong, those guys will end up, you know, being expected to give eggs, and the girls will be expected to produce eggs in a different way. Anyway, it's very important in the chick industry to separate at early stages. So what people are doing is they go to the college, and they learn how to do this. The problem is nobody knows how to explain it. Like, you cannot have a tutor that knows and explain it to you how you recognize it. I think they are like touching it. I don't want to know, to be honest. Anyway, there are people who know. They have seen a chick, they touched it, they did something, and they know. It's just something they're born with. Or something they're learning in this college. And in this college, it's not like this tutor is, as I said, explaining to it, because they cannot explain. It's inexplicable. Yeah. What they do is sit next to the student, and the student is supposed to guess. The student is supposed to make the best effort. And the teacher is saying, you're right, you're right, you're wrong, you're wrong, you're right, you're wrong. Apparently, after a few weeks, the mind is rewiring, adjusting the coefficients of the model. After a few weeks, the student can be a chick sexer and earn a lot of money. So, to finish on machine learning, we have problems like classification and regression. So this is supervised learning. So we have those labels there. We know there are an underlying truth. Like with those movies, we had the labels so we could you know, predict other new examples like Gone with the Wind based on the previous data and based on the previous labels. On the other hand, we have unsupervised learning. This is something much cooler, and this is something that is taking on nowadays. And this is more like finding the patterns through those data and having those bright moments like John Nash had in the movie. The thing is, it's very hard to evaluate, because if you don't know the underlying truth, if you don't know the right answers, if you don't have labels, how can you judge that you're doing okay? So there are some statistics, there are some papers, of course, on that, but it's very interesting, very uncertain area at the moment. So let's go to the R language. I don't know if you remember this Big Bang Theory episode. They had this problem, and they said, this looks like something aliens dropped that we cannot understand. So this was my feeling when I first encountered R. I was a C# developer back then, and R was like, I don't understand, I don't know how does it work. Apparently, if you're coming from mathematics, statistical, even business background, you're getting the feeling of R as something natural. So I'm guessing I don't have this background. This was language not created by programmers. This was the language created by mathematicians, by statisticians. And it's very good for this exact purpose. So why would you use R? For data wrangling, for data modifications, transformations. It's pretty straightforward once you're, there. Once you're over this learning hype. And it's very good for machine learning. I've seen a number of talks and even like workshops where people are teaching you TensorFlow, but for example, using R for linear regression, because it's that simple, that's straightforward. This is an actual statistical language. So if you're using statistical models, this will be very straightforward for you. We will be using R for machine learning process. Let's look at the supervised machine learning process. First, you get the data, then you have to clean it, then you have to pre-process it, and if you're a practitioner, you're like in the almost endless loop here, and then after like few days, weeks, you finally go to another stage, and you can do fun stuff. Oh, maybe not that fun. First, you need to split the data to your training and testing, probably even validation set. Then you're doing the fun stuff. The fun stuff is here. That's why I made it very big. So machine learning algorithm, this is where this magic is happening. And then once you have a trained model, you can score it, you can evaluate it. The question. I have both arrows that I'm scoring and evaluating training and test data. How should you evaluate your machine learning algorithm? Which data? Yeah, why test data?
Because you use the training data to effectively tune the algorithm. So if you then use the training data again, it can be exact. You'll overfit.
Yeah, so there is this concept of overfitting. If you've never heard about this, it's a glorified name for an algorithm can learn the examples by heart, right? So if it's too good on the training data, it won't be very good on the test data. And this is this whole art of splitting the data properly and doing all of cross-validation techniques, et cetera, et cetera. So first problem I will tackle with you and R will be classification problem. So in this data set, for those of you who don't know, it's like a hello word for deep learning, but I will use it for a classical classification problem. We have a set of handwritten digits, and we will try to classify a specific digit. Digits may sound mathematical, but it will be a category, a label. So those will be labels from 0 to 9. We'll apply the model, train the model, and then evaluate it on the test set. Those digits are not 28 by 20, 32 by 32. This is not a nice data set, I was wrong. This is a different handwritten digits taken from UCI database. So it's 32 by 32, and they were compressed to be 8 by 8, so we have 16. So we have 16 input values. There's another question: which algorithm to use? So first algorithm that is in every introductory machine learning book, very known algorithm, is k-nearest neighbors. So I will teach you this algorithm here if you don't know it. What's the color of the green spot? Why? Blue, right? Why? We have 3 blue neighbors and only 2 red neighbors. This is k-nearest neighbors algorithm. So we are calculating the distances to all the data we have, and we are taking like k-nearest, so 5 nearest I chose here. You could take 7 nearest, 9 nearest, why not an even number? Because we want to have a specific decision. If we have an even number, there can be a situation that we have half and half and we don't know what to do and the algorithm is wrong. And then we're just saying, oh, so most of the neighbors were blue, so my dot is blue. Very simple example. How to evaluate this method? There are plenty of statistics. If you're a statistician, that's fine. If you're afraid of math, this is the simplest math you can ever get in the machine learning space. So if you're scared, just calm down, go home, learn a little bit of math. It's just counting, dividing, adding, nothing really scary. So we have stuff like accuracy. Accuracy is how many times we were right divided by number of examples. So we can say we have 90% of accuracy, or our algorithm was accurate 90% of the time. And what does it mean? Well, it means something. It's better to have a higher accuracy than lower accuracy. But if your classes are not balanced, let's say we are classifying if somebody has a breast cancer. And let's say only 2% of the people will actually have breast cancer. If our algorithm is saying nobody has a breast cancer, it's just coming with false answer, we will have 98% accuracy. So depending on classes, depending on the balance of the classes, depending on the model, depending on the problem, accuracy says something, but, well, it really depends what do you want to achieve. There's another statistic, area under the ROC curve. I think there was a talk yesterday on a ROC curve, so yeah, you can probably understand more from this talk than me talking about this for 10 seconds. The basic thing with area under the curve is it should be like as close to 1, so the area that is under it should be as close to 1 as possible. So let's classify stuff in R. For those who see the R for the first time, yeah? That's like aliens, some characters, very weird, very weird. But to be honest, classification takes this one line. This is the classification part. The first part is reading from the CSV file, reading those digits, and then I'm actually saying that the last feature, I want to convert it to factor. Factor is a category in our language. So I'm saying this will be a label, and I'm saying predict this label based on the other data using the training set that I've just read, using k-nearest neighbor algorithm. This will be my model. And believe me, it takes a few seconds. Then I'm saying, okay, we have this model that is fitted. Take my test set, take first 64 things, so don't take the labels into account, and predict stuff. So this is it, 2 lines. This is machine learning, this is evaluating. And this is my confusion matrix. Confusion matrix is telling you, well, basically, how many times and where did you miss. So you can see for different digits, for like 0, 100% right. I'm looking for something like 8. 8 was 93 right, and it was very often confused with 0. So you can see with the confusion matrix, displaying this, visualizing this in nice colors, it took me more than one line, to be honest. You can see my code in the GitHub repository. But there is one line thing that says this confusion matrix, this function, that will give you the same data just in a text form, not with the nice visual form. Okay, second problem, regression problem. Regression problem, in comparison to classification problem, is not predicting the labels, not predicting the closed set of categories. It will just predict some real number. So if you want to predict how much you should sell your car for, or how much will it cost to, I don't know, how much you can think your rent would be if you buy this and this property, this is your regression problem. And a little bit more math. Linear regression problem, ordinary linear regression, is trying to find the line that is fitting the data. And the thing with linear regression problem is it's a horrible model. Like, every statistician will tell you it's a horrible model because our data rarely is linear. And what will this model tell you? Look at those examples. For those dots, it will find you this line. For those dots, for these dots, it will find you another line. But these dots are not linearly correlated, right? This model is very sensitive to some values that are just a mistake, right? And even if you have some data that we don't know, actually, we shouldn't even think of it as a regression, linear regression problem, it will still give you the line. Because machines have this one thing in common. If you're putting some numbers and saying, run this function over those numbers, you know what? It will give you some numbers back, right? It will give you the line. It will give you the coefficients. So I'm just appealing to you. This is my route. Before using specific function, maybe even before using machine learning at all, you should really think if this is the solution to your problem, if the data are in the proper shape, if maybe hard rules will be better. But yeah, that was just a digression. So let's say we have a proper data and we want to find this line. There is an analytic, solution to this. So if you're summing all the differences between the numbers, between the dots and the line, and then, this is some linear algebra, you can use it as a loss function and you can optimize it. And there is an analytical solution, so you don't have to run actual gradient descent or anything like this because you have an analytical solution. The problem could be if you have a lot of dimensions and a lot of data, and if your data are linearly correlated, so some libraries and some statistics won't handle it. But our will. And we have some other statistics that can tell you how good your model is. Like with classification problem, it was quite easy to grasp. If we have high accuracy, let's say our classes are balanced, the biggest accuracy, the closest to one, the area under the ROC curve is, the better. And the problem with evaluating linear regression is we're saying, okay, my data differ from the line. But what's my scale? Is 5 a good number? Is 500 a good number? It's not that easy if you're not a domain expert to evaluate it. So there is another statistic, the R-square, that is taking the average stuff, summing, dividing, etc. The better to one it is, the better your regression model is. But it's still now not very easy to grasp models. So it starts to introduce some complexity, the model itself. So let's see it for the Prestige dataset. Prestige dataset is the dataset that is included in our package and basically has the data on education, income, how much percentage of women is for the specific occupation, and there is a census number, there is a type, so if it's a blue-collar professional or white-collar, and we want to predict the prestige, which is some index, which is some real value. And I did the pairs function, you can see it here. So I said, use the pairs of a prestige and plot it. And those colors you can see, those are the types, so blue collar, white collar, and professional. So what I can see is, when I look at prestige, is that maybe women don't matter that much. Don't get me wrong, women matter, but maybe the percentage of women in a specific industry or specific profession doesn't matter for the prestige index. I would say like education is kind of linear, if I'm really stubborn, but not really for like income. It's more like quadratic, right? So I would like to run the linear regression. So what I did was I actually included women, and I did the logarithm from income. This will straight up the line. And I ran linear model. So LM, linear model, that's how easy it is. I'm saying predict prestige, fit the line to prestige based on education, logarithm of income, and women using the prestige data set. And then I just did the summary. So R is very useful, and when you look at this, you may, if you're not a statistician or if you haven't worked with linear regression, you may not understand what those things mean. But if you are, if you look into this statistical model, you have all of the statistics here, and they even tell you which features are actually significant. They even give you stars. You can have 3 stars, you can have 2 or even 1. So this is intercept, so basically this doesn't matter, but it just told me that women probably is not significant. So another thing is, I only looked at the correlation between those things, but we actually should look for another regression plots and see if our data actually fit. But I will move on because we don't have that much of a time, right? I will skip through categorical data. So let's say I won't explain the theory, but let's look at how R can help you with categorical data. So I plotted prestige again based on education, income. I threw away women, and I put type. And type was a categorical value. So it had blue collar, white collar, and professional. And what it created was 2 dummy variables. Because we have 3 values in our three values in our categorical data. So it created 2 dummy variables. So it basically created variables that have zeros or 1. And the thing is, you can do some miracles with it and like plot. I just plot prestige, and those dots are by the type. So I could separate my data using categorical data, using linear regression, and think of how this prestige actually look like for specific profession. And linear regression will give me those answers. A lot of math? Too much? No? Oh, you're a great audience. Usually people are like, just move to something less demanding. I'm actually moving to something a little bit less demanding, and I won't give you a lot of statistics, but the third problem that is not supervised learning problem, which is a clustering problem, very classical. And we have different algorithms to tackle it. The most popular is k-means, which I will walk you through in a second. And my problem with clustering is once you have clusters, you can run some statistics like are those dots near to the clusters, are they away from other clusters, and you can kind of evaluate how it is. But in most tutorials, you see those pretty 2D pictures. And to be honest, if I have a pretty 2D picture of my data, I don't need any machine learning algorithm to cluster it, right? I would just do the circle here, circle there, and have my clusters. And the problem with clustering is it's very hard to verify if it did a good job. If you think of market segmentation, which is a classical clustering application, you know, the market will verify if your algorithm was good. So the business will verify it, and it's not even that sure. So k-means algorithm takes the data, and I want to split my data into 2 clusters. So I'm randomly putting the centers of those clusters, and then calculate the distance of every single point to both clusters. And the one that I'm closer to, I'm just coloring or assigning to this cluster. Then I'm looking at those clusters and try to calculate the new center based on my data. So my centers moved here and here. And you do it again and again and again. You can just run it from thousands of iterations, or you can just run it to the point when nothing really changes that much. And basically you have your clusters. There are different algorithms to initialize the data, to put those random centers, etc., but basic idea is this. So I will show you how you can use clustering and R for the Chicago crimes data set. It won't be very real-life example, although it's on very real data. So Chicago crimes data set has like a lot of stuff, case number, arrest, primary type. So this is the data set that you have to throw away a lot of data because it has a lot of like IDs, which are not really meaningful in a data, in a machine learning process. So what I wanted to do is I just wanted to plot it on the Google Maps and show you how kind of easy it is. So what I did first, I just selected the crimes of the type 2 and 4, which is assault and burglary, because when I plotted the data with all of the types, it took ages and it was just a bunch of dots, and that didn't tell me anything. So now I'm taking the libraries ggplot2 and ggmap, which is basically Google Maps, and I'm saying, get me the map of the mean value of my longitude and latitude of those crimes, which basically will just put it in Chicago area. Zoom it. I just tried different zooms, and zoom 11 worked to grasp most of the Chicago. And map type terrain scale 2, and add my points from my selected crimes from longitude and latitude, and color them based on type. So we have assault and burglary. It's not a very pretty visualization, but it was pretty easy to actually get this. So underneath there is a Google map, over that there are points. Then we can get clusters. So k-means get my selected crimes and just, you know, take longitude and latitude and put it into 6 clusters. That's what I did in this first line. Then I get the centers of the clusters, then I put some colors, and again, I plotted a gmap, and then I put points of my selected crimes. You know, this is a very nice visualization. But, and everyone, when I talk clustering and ask, what would be the nice example? Everyone says crime data, but I'm like, really? Thank you, machine learning. I couldn't do it myself, yeah. That was really, really great. So this is the example how easy it is to use R or any library for the task of machine learning, which was completely unnecessary. I could just plot it, could use the just plotting, and just say, oh, this is one cluster, this is another cluster. I could do it myself. I don't need machine learning. So with this optimistic point, I would like to summarize that we talked a little bit about machine learning. You were much more active than my presentation before. We went through the classification problem with handwritten digits recognition, regression problem with the prestige data set, and with me putting something to think of about the clustering problem. I hope you found how easy it is to use R once you know R. It's a very, very useful tool. And yeah, if you want more, look at my GitHub repository. So thank you very much. That's it.